Hello, everybody. Can you hear me? Okay, perfect. So today's talk is going to be fairly short, I assume. So you'll get a little bit of extra time for coffee and stuff, or maybe write in a new Parse transformation. I don't know. Anyway, let's start with it. So the idea behind Parse transformations is that the goal of Parse transformations is completely opposite to goals of plastic surgery. So it makes nice code look ugly or just a little bit uglier than it was initially. Why would you need that? So the idea is that you don't want to write that code. You don't want to see that code, and yet you need it. How do we do that? What is the example? Why do we actually need to care about some parts of our code in that way? Let me show you something. Probably a lot of you have seen situations like this. So for example, we're dealing sequentially with some sort of list. Let's say that specific list. And we ran some map function on it. And we got L1. And then we need to do something else on it. So we take L1 and get L2. Great. Looks great. When you have 20 of those operations, you'll get L20, L21, and when you try changing them, it's getting really, really, really funny. The other example is actually fairly common. In Cowboy's API, every function call that works with a request, whether it's a mutating or non-mutating function, it always returns a possibly updated request object. And certainly you can deal with it the very same way, req1, req2, and when you have 50 lines of code, well, you have a lot of request objects to handle. That's not right. So instead of that, how about we write our code this way? We say that we have kind of special variables. We'll just have an add sign as a suffix for that variable. And see what we have. We have the very same variable following through the code. So it's L, everywhere just L, and everywhere just rec. So it looks like we are actually breaking the single assignment rule in this example. How do we do that in Erlang? Good question. Well, we have a parse transformation that actually changes it from this to this. As we can see, it has 0, 1, 2, 1, 1, 0, 2. So it actually enumerates it for you. So something that you do yourself usually, it just does it for you. Well, if you think about it, computers are better at enumerating stuff than we are. And they're faster at it as well. All right. So how do we actually do this? So the example is clear what we get, but how do we get there? There is an answer. Basically, it's some sort of meta programming. A parse transformation on its own is basically just an Erlang module that takes another module and rewrites it. So the module that gets into your parse transformation is represented in abstract format. And what abstract format is just a list of tuples, as you can see on the right side, hopefully you can see it, where every tuple represents some part of the parse tree. So it takes that and processes it according to a specification and produces something. Let me show you something. So here is a function, just an arbitrary function that actually is completely pointless, but the point here is to show how it looks like when it's parsed. So let's just memorize this. It's called myFun. It has an array of 2, some weird arguments, and it just prints them out, essentially. So this is how it looks like. A little bit verbose, right? But actually, for the trained eye, it's not too bad. If you look further, here's the definition of your function. So it's myFun with an array of 2. Let's go further. Well, here's our tuple of an atom command and a variable x. Here's a variable args. So just like in the example, we had command x, args. We have them right here. What do we do next? We do a call to IO format with that string that we saw there, and this list, basically the cons. So you can see X, args, and an empty list, which effectively is just X and args. And it's fully reconstructible with one of the Erlang modules that ships with Erlang called ErlPP. So you can actually get the very same source code with minor differences such as spaces, and obviously you won't get your comments back, but you can actually get your code back from that parse tree, just like I did with this example. So in a bigger picture, the general workflow, how parse transformation works, is it gets the whole parse transformation tree, the whole parse tree, and then it's basically traverses the whole tree, going down through every element and seeing, well, does it match to what we actually are looking for? If it does, rewrite it. So let me show you another completely pointless example. The example here is that we want to rewrite all the occurrences to some magic function, to calls to some module, not so magic function. So this is how you do it the normal way. So you find a function, you proceed on processing the first clause, you get down to the body of the function, which is the actual code in the function. And then you go through every expression and see whether that expression is an actual call to that magic function. And let's assume we didn't find it there, or it doesn't matter. Then we proceed with the second clause, go down again and again and again and again. We're just traversing the whole thing. And we're repeating that again for another clause. So it looks a little bit unimpressive. It really makes it hard, and nobody really wants to write that. Well, there are actually some solutions that do help. Ulf Rieger actually wrote a tool called Parstrands, and you can find it on GitHub under ESL's account and I believe Ulf's account as well. So what it essentially does, it does that mundane traversing for you. So that means you can get to pretty much any level of your code really fast. It also allows you to inject new forms either before or after elements that you're replacing or just keeping as is. And it comes with a few interesting examples and extensions on its own. So you don't need any of those things for our simple pointless example. You just do that. So here, you're just matching on an application, an application considered a call, basically. So you see a form of a call happening on the line L0, and the atomic name of that function is magic function, and we have some arguments. We don't even care about their arity. We're just looking for any call to magic function. And what we do here, we effectively say, well, this element has to be replaced with a call to some module and not so magic function. And we're saying, well, continue on. Here's it's a recursion. Continue on, go deeper, investigate what is there, and we'll do the job. So effectively, your whole code for doing that specific transformation that we have been discussing is just those 3 lines of code. Pretty impressive. Another thing that ships as a very good example of using parse transformations is Exprex. So what Exprex is, how many of you dealt with records here? Good. How many of you know how frustrating the fact of having record info working only compile time? You can't really do anything runtime. Good. Because Exprex actually, what it does, it goes through your module, understands all your definitions for your records, and basically generates some code for you so that you can retrieve the name, the list of the record field names. You can also use some helper functions to create new records, so you don't need to know compile time, what exactly you're creating there, and change some of their values. So it's actually pretty impressive, and you don't do anything on top of it. You just include that parse transformation. So all the magic is actually behind the curtains. I love it. Actually, for some use cases, it's a fantastic tool. Let's go further on. Here is an interesting realization. So apparently, the source code that you write and then pass to your parse transformation doesn't actually have to be compilable as is. All it has to be parsable. If it parses correctly, then it will go to your parse transformation. What would that give to us, you might ask? All right, let me show you. So this is a typical example of a very simple Erlang module, right? And we all know how frustrating could it be sometimes to jump up and down to update the signatures of your functions or remove some functions, add some functions, change their names, especially if your module is, say, 2,000 lines of code. You just have to jump up and down or keep two buffers open next to each other. That's not really efficient. So how about we do something like this? We can actually do things that are completely unallowed in Erlang. So we say, well, here's a function that has an argument of a function head. And then there is an implementation and even a guard. So what this does with the parse transformation called Exportie, it converts it exactly to this code. And obviously, if you'll try to compile that, you will never have anything compiled. So how does that work? Luckily, the tool is really, really simple, so I can actually show you in detail, pretty much step by step, how is that accomplished. So let's start with the state that it uses during the parse transformation. So besides the options field, which is not important in our situation, what it has, the most important things are this exports field, which collects the functions that you want to export, and it also has an export keyword that you want to use. The reason for that is this. So here we have it. If you actually want to change it for any kind of aesthetic reason, for example, you want to rename it to export this, and don't type any characters like at. So you can actually do that, and you'll see how very briefly. So this is the entry point of the parse transformation. So what it gets all those forms as the first argument and some compiler options as the second argument. So what we do here, we actually use Parstrands to go through our transformation callback called doTransform. And that's the most interesting part of what's going to happen there. So let's start with the redefinition of that export add syntax. So all you have to do, you have to define an attribute called Exportie and put any item you want and use it from there on. And the whole implementation of this is just these two lines of code. So what it does, it detects that there is an attribute called Exportie, and it has a certain value that we call custom. And basically, it keeps this form as is, and all it does is just changes its own state. So we just know what Exportie do we want to use in our module. This is a more interesting thing. So here, what do we do? Whenever we detect any kind of function, we go into a deeper transformation layer. We'll call it export transform. And it's the very same kind of function as doTransform. We just go deeper into the recursion with this function. And the whole implementation of this function is just these three clauses. Let me explain to you what they do. So for every function, obviously, as we have discussed this before, we see the clauses for those functions. And every clause has a head, which is H here, a list of guards, G, and a body, B. But what we actually do, we just go and transform only the head with our own export transform rule. What this means is that when the Erlang source file gets parsed with the example like this, export this, my font. It actually doesn't know exactly that it's a head of a function. So it thinks it's just an application of another function over there. And that's what we match on. We say, well, if there's an application of a function called any name, basically, with any number of arguments, but within this scope, then we return that function name and the arity of that function in our state. And there is a default case that does nothing. So after this, there is a default case into a transform that, again, does nothing. It just keeps the code as is. So what this means is that when we have this function, the export this myFont, it records the fact that myFont is an exportable function. And if you look into the result that this clause returns, it returns only args. Why is that? Because the args is our function invocation, or something that Erlang parser believed to be a function invocation. So it leaves an actual function definition over there, and that's kind of great. What are other uses for parse transformations? So one of the uses is compile time analysis and extractions. So for example, when you can't really analyze your module runtime, for example, for some performance reasons, or you don't ship your code with debug info included, so that you don't really have any parse tree available at all, you can just do your analysis and extraction of some important information, just compile time and forget about it. Code instrumentation, there is an interesting tool called annotations. I personally haven't used it, but it looks interesting for some uses when you want to do some level of indirection in your code. And obviously for building domain-specific languages, on top of Erlang with Erlang-ish syntax, but with a little bit of different semantics that turns out to be an Erlang code later on. And last thing, do not abuse this technique ever, 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 ever. You will certainly regret this. Thank you. Any questions?
What limitations are there in terms of doing the syntactic parsing before it reaches the parse transformation stage? Like, you can't just put arbitrary punctuation and symbols anywhere you want, right?
No. No, it still kind of has to be sort of valid, but there are just some flexibilities in what you get so that you can do tricks like that. So well, in my experience, obviously there is a source code for the parser, but in my case it was just trial and error. What can I do with it? So can I do that? Okay, that's kind of cool. If not, well, proceed with something else.
So you caution to not abuse it. Can you give an example that you've seen, or from your experience of maybe using it too far, where you feel like, now this was abused and not used?
I guess my rule of thumb, like I can't really give a good example off the top of my head, but the rule of thumb would be if you use parse transformations deliberately in your own code, so you write your own parse transformations for more than 2% of your code or something like that, then you have to be just careful. It doesn't necessarily mean you're already in the red zone, but it really has to be, basically you have to have a really, really good justification. So if your thinking is, well, it would be kind of cool, then probably you shouldn't use that. Because it will lead to a code that actually is something different later on. So you effectively obscure the connection with between the actual code and your source code. So you must have a good reason for that. If you don't, well, you're on your own, I guess. Any other questions? I guess not that.
No.